Hi everyone, in this tutorial we are going to be talking about cyclooctene. Okay, cyclooctene, an 8-membered ring with 1 double bond. What's kind of interesting, and this is something that we talked about earlier in the video series of stereochemistry, we said that double bonds within rings, 3 through 7, so we'll say 3 through 7, double bonds within a ring could not be E/Z, because there was no E stereoisomer that was actually possible. But what's interesting here is with the 8-membered ring, cyclooctene, we can have our Z stereoisomer, and there are now 2 E forms. I'm going to call these E1 and E2. Okay. What's interesting is E cyclooctene is helical. It is helical, and as a result, it actually has a non-superimposable mirror image helix, hence why I'm using this designation of E1 and E2. Okay, so we have Z cyclooctene, and then we have E helix 1, E helix 2, and thus there are 3 possible stereoisomers for cyclooctene. All right, we are now going to go over example number 10 and example number 11 to reinforce this idea. So again, we're looking at our cyclooctene. This is 8 members in the ring. Now there's going to be 6 possible stereoisomers because now we have an asymmetric center as well. Okay, so here you could say we have the Z, we have the E helix 1, we have the E helix 2, and the asymmetric center could be R or S. That is 2 total possibilities. We have E helix 1 capable of having the asymmetric center also be R and S. There's another 2 possibilities. And E helix 2 could have the asymmetric center be R or S, okay, which gives you then a total of 6 possible stereoisomers, okay. Now, another way that you can safely do this calculation in most cases, okay, is to take this idea of having the Z, the E1, and the E2, and multiply 3, that's the number here, 3, by the number of asymmetric centers, okay? But what you're going to do is multiply it by 2 and by 2. Say if you had 2 asymmetric centers, you would multiply 2 times 2 times 3. So here you could say we account for the 3 for the Z stereoisomer E1 and E2 times 2 for 1 asymmetric center, and that gives us 6 possible stereoisomers. We're going to prove that here with this compound, okay? We could say cyclooctene. We have our cyclooctene molecule, therefore it could be Z, E helix 1 or E helix 2, and now we have 2 asymmetric centers in example number 11. Therefore, we could take this 3 value times 2 times 2, accounting for each of our asymmetric centers there. So that would give us a total of 12 possible stereoisomers. If you wanted to prove this out for yourself, okay, you essentially could have the Z have RR, RS, SR, and SS. And you could also get those same 4 possibilities for the E helix 1 and E helix 2. Right, we have 4 possibilities for RS combinations, another 4. 4 plus 4 plus 4 gives you 12. Okay, I want you to go back and watch this video again to reinforce this idea. Some professors test on cyclooctene, and it is very helpful to know it. The quick recap is cyclooctene is special. It can have an E-alkene stereoisomer, which is a helix which is chiral, so it can have its enantiomer. Therefore, for the unsubstituted cyclooctene molecule, there are 3 stereoisomer possibilities. If you then think about substituting that cyclooctene molecule with asymmetric centers, meaning we've added groups such that there's now asymmetric centers, you would then multiply by 2 for each asymmetric center. You multiply the 3 that we derived here by 2 for each asymmetric center. 1 asymmetric center, 3 times 2 gives us 6 possible stereoisomers. For number 11, we have 2 asymmetric centers. We'll take 3 times 2 times 2 to give us a total of 12 possible stereoisomers.